Would you be interested in watching a video of robotics work from the play that I was advertising like a couple weeks ago?
We can do whatever you like.
Okay.
Yeah.
So I'm going to play a short video set to some 90s music for you, and just to kind of show part of the robots in this play. So let's talk about our next 2 weeks. So already next week is fall break. So being aware that this is the class like in the afternoon right before fall break starts, just to give you a heads up, we are not going to meet on Wednesday. So if you want to start fall break early, I don't want to be the thing standing in the way. I'll be in my office. If you need anything, feel free to stop by. But just consider it a day to work on the challenge. Challenge 2, I'm told, will be released on Monday. And I think it will be, but we're still working on a few details. But I can tell you with the basics of it are you'll implement a stack. And I'll post the code on Canvas of a stack and a queue. Yes?
I think your dates are all, it was like 13, 14, 17, 15.
Oh, yeah. That's nice.
He needs some extra credit.
Good. Yeah. Thank you. Does that look, yeah. Okay. Does that look better? I think that's right. Okay, thank you. So yeah, the challenge will be released on Monday. It'll be a stack, and the thing that you'll do in lab, I believe, is convert the stack into a queue. And if you remember, like that's just like switching a couple of things because one is last in, first out, and one's first in, first out. Either way, on Canvas, I will post later this afternoon, actually, the code for both a stack and a queue. So you'll have that code. It's just a matter of you like going through it, understanding it, and then knowing how to convert one to the other.
So we'll have a working stack.
Yeah.
And we just look at the queue and change the stuff in the stack.
To make it behave like a queue, yeah.
So then when we go to all we gotta do is memorize it.
Yeah, I mean, you know, if you want to think, you think about life that way, you just really just got to memorize a lot of things and say them at the right time, right?
Yeah.
But yeah, that's what it'll be. There may be like one extra detail or something about like maybe it will be like strings instead of integers or something like that. But that's the general thing of what the challenge will be. We'll release it on Monday, and then because of fall break, it won't be due until the 18th, that next Friday.
That's immaculate.
Yes, and so in case you are like thinking way ahead, I'm thinking like in here, like a week from here, like an exam maybe on a Wednesday, which would be basically it will just be binary search trees and heaps, which will cover heaps.
So, wait, we thinking 3 weeks from now.
Yeah,
After
yeah,
the 16th.
yeah. So don't worry about it. I mean, for me, that's like an infinity away. I know some people plan further out. If you plan further out, that's the week where the exam is likely to fall.
I got life planned up to 6 o'clock today at Bulldog Bad.
It's pretty good. I mean, I don't know. How far ahead do people plan? Who plans like a week ahead? Anyone lower than a week ahead? Okay. How about like a month ahead? Okay. Anybody higher than a month ahead? A few things. Anybody like got like a hard cutoff on when they're gonna like find their life partner and get married? Or, you know? No, I don't know. So yeah, I usually kind of keep us about 2 weeks ahead, and then I know kind of what we have to do in the semester. So that's where we're at with everything there. And we'll just consider Wednesday a work day for the challenge. And then when we come back from fall break, we will like recap the trees because you'll probably have forgotten them. And then we'll talk about heaps for a couple of days. We'll have a review day before we have an exam. Then we'll have an exam. And I'm trying to make it so that the exams don't fall ever when a challenge is due. And that's kind of one of the like difficulties with this being Monday, Wednesday, Friday, which is that the challenges can be due on a class day. And so, yeah. All right. So are there any questions about this, concerns? Okay. Great. So if you remember last time, we were looking at binary search trees, and in case you have forgotten or were not here when we discussed the binary search tree, it's really a very basic idea. And the idea of the binary search tree is it is a tree. It's this node-like thing. It always has, at most, 2 children. And the principle that we follow is that when we look at the tree's left side, that child's value is always less than the parent, while the right is always greater. And you can apply that to any data type. We're going to use integers because it's easy to look at and say what's less and what's greater. But anything that you can write a comparison for, you could use as the value there. So we were building that, writing that code for a binary search tree in C++, and we were following the standards that Challenge 3 will use, so that you'll be ready for that. So today we'll continue that. To kind of remember the basic idea, here's our tree structure. And the way that we're abstracting it is the first thing we're doing is we're making this node class, kind of like we've used in linked lists before. And the idea is like each of these is a node, right? And a node will have a data value, and it will have a left and right child, in our case. And so those are nodes. These nodes connected together, that bigger construct we'll call the BST class, binary search tree class. And we'll break it down like this. So in terms of like the files that we have and in the code we're writing, we'll have just like, here's our test C++ file that we're writing, so that's where our main method will be. That's the entry point for everything. That will include the binary search tree that we're writing. And then binary search tree will include the node class that we're writing. So that's kind of that structure, just to get you conceptually oriented on that. And if you remember, we had this nice list of headers that was provided to us for the challenge. And we had a list of private and public methods that we wanted to implement. And so the idea being that the private ones will be used within our class, the public ones will be used by things using our class. And kind of to illustrate that idea a little bit, you can imagine like here's our main method, like our main C++ file, main method. We create a binary search tree and we call something like insert. We call the public version, which in this case just takes data, right? And that actual implementation of that we'll call a private version, which takes 2 parameters, a node and data. And it will take care of doing the work of passing the root node in for us. So if we're using this in our client code, we don't really have to worry about what happens in here, but because we're writing this, we do have to worry about what happens in here. And so we note that we should not be afraid of these things. These are pointers to references, and they're a convenience that lets us write this recursively so that we can set the value of like ancestor nodes without having to get out of a pure recursive approach to it. So it's just letting us have access to a variable where we need it. All right. And so we started writing the node class, and that looked just like this. We had some public fields. We had just the int data. Then we had 2 pointers, a left node and a right node. So 2 children. We had a nice default constructor here that sets everything to 0 or null. And then we had a constructor that will take the data in and set the data to data and the children to null. And then there was one method that we wanted to implement for node, and that was the degree. And so if you remember, the degree of a node is just how many children does it have. So in our case, we can have 0, 1, or 2. And so we wrote that method. So I'll switch over to our code now. Let's see. And pick back up where we were. So we'll start with just taking a look at our test file. So this is just our main file we have here, and so far, like, we've written just really nothing. We've got a main method, we've got a cout telling us that we're running this, and at this point, we had included node just to test things, and so if you remember our directory structure, just pull it up in the terminal. So what we have in our directory, we've got our test file, where our main method is. We've got node.h, node.cpp, bst.h, bst.cpp, and then we have an a.out from when we compiled and tested it. So since we have set up most of these, and I'll just switch over to show you, we have node just as it was on the slide, and then we had written the degree function for node, and so that looked like this. It just returns an integer, and the way we did that was we created a count variable, and we said, if you have a left child, +1, if you have a right child, +1, and then we return the count. So it's either 0, 1, or 2, and that's the only method that we needed to write for node. So we did that, and then we have our BST, our header file here, which is just exactly what we got from the challenge requirements. And we had started to write our first method in that class, which was our private insert method and then our public insert method. And so I'm going to pick back up, since we wrote these, I'm going to go ahead and jump over to our test file. And rather than including node, because we were just doing that to make sure that node worked, I'm going to change this to BST because that's what we'll actually use, and that's what we want to know that it works with. And so I've got up here in the comment, I like to just put this at the top of the file because I switch between a lot of things, and it helps me remember, like, if I want to compile this thing, this is it. And it can be nice to leave little notes like that in comments if you're not like, if you're having to switch between things a lot, it's helpful. So this is how I'm going to compile it, and when we compile these, the first thing I'm doing, I'm calling G++ as the compiler I'm using, which is aliased to something else, but calling G++, I'm specifying this argument here, the --std equals C++17, so that I get the right standard of C++, and that makes sure that I can use things like null pointer. The next thing I'm specifying is the main file, so test.bst.cpp, and then I'm doing each of the CPP files that we're using within here. So even though I don't directly use node from my test file, I still need to list it here because of the way that dependencies work. And then I'm just specifying a name for the output as test.bst, and then that will let me use this approach to run it. So I will copy that, and let's put it in the terminal and see if that compiles. It looks like it compiles, and then see if it runs. Okay, so it's running, all right. Oh, just as an aside, how many of you know like tab completions in a terminal? So if you don't know this, it will change your life for you. So like here I've just got a list of like files, right? Anytime I want to like get kind of autocomplete, like if I just start typing like NO, if I hit tab, I will get like a autocomplete. Let me give it a, so like say I'm calling G++ on test, and I hit tab, it'll autocomplete for me. And so that's kind of fun, like if you, I'll just give like a random function. So see, like if I just keep hitting tab, it's just going to go through like everything that could be possible. But this will greatly speed up things for you. If it's not something you use regularly, try it out, and it works just, you know, on anything in the terminal. So you don't have to like copy and paste like, you know, paths and stuff. If it's just like right there, you can just tab, 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 and like, you know, you can also like say you want to go somewhere, like I want to just go into my users directory, I can tab users. I know that Zach is mine. Maybe I have like documents or something. Oh, okay. So then there's like all the D choices, so I can type in like DR, Dropbox. You know, it'll just keep going with me. And so very fast, nice quality of life thing. If you don't use that already, try it out. Okay, so we've done that. We've compiled it and run it, and the test file is working just fine. So let's move on, and let's work on doing, we've done insert on our BST here. So we've done the private one and the public one. Remember, the public one is what's called from our test file, and it just specifies the root as the root and calls the private one. And so the private one does exactly what we would think. It comes into the tree. It sees if we're at a null value, then that's where we're going to put our new value. If we're not, then we need to see if we should go left or right. And so then we fall into these conditions. Either we go to the left if we're less than, or to the right if we're greater than. And so what we do is we recursively call this until we get to null. So we find the spot that we want to put our node. Okay. So if you remember, remove has quite a few different conditions. So it depends on the degree, right? Like it can be as easy as just like taking a node off the bottom of the tree, or you can have to swap some things around. So let's go ahead and write that. I will start with the easy part of it. So I'm going to do the public method, or the public remove method. I guess I should call these functions in C++. So we'll do the public remove function. And if you remember, that's a Boolean, and it's BST class, and then remove. And so it just takes in data. And this is what we'll call from our main file, and it will just say what node we want to remove. So all this function is going to do is call the private version of the function and specify the root of the tree is where to start. And so to do that, we're just going to return the value of remove. And you can see kind of IntelliSense has popped up here to tell me that I have two methods called remove, so 1 and 2. And the reason they're different is the parameters are different. So the public one just takes data. The private one takes a node, which in this case I'll use root, and the data. And so we'll call that. So that sets up our public interface for this, but we actually have to write it now. So we'll need to do the private one. So let's go ahead and start on that. And I will try to do this as best I can in this constrained space. Let me know if this is not visible or if it scrolls out of where you can see. Okay, so let's do the private remove function. And so it's also a Boolean. It's in the BST class, remove, and it takes in a node. And remember, it is a pointer to a reference of a node. And so that is what that beautiful syntax means. Okay, so here we are. We're ready to remove something from this tree. And what we get in is we get a reference to a node in the tree, and we get a value that we need to look for and delete. So the first thing that we're going to do is cover our base case. Since we're doing this in a recursive fashion, we need to think about, so first of all, it might not be in the tree, right? Like somebody might ask to remove something that's not in there. Okay. So that will ultimately result in the node value being the null pointer. So if that's the case, some extra brackets. If that's the case, then all we need to do here is just return false, because there's nothing to remove. So we will return false to the calling method, which is that public method, and it will return false to whoever called it. So just along that chain there. Okay. So then, now we need to see, there are a couple conditions, right? So either the node we're at could be the thing we need to delete, or we could need to check the left and the right of that if it's not. So let's cover those cases of the data not matching the node we're currently at. So we'll start with, let's say that our data is less than the data in the current node we're looking at. Then we need to essentially move down the tree, right, and look for this data where it might be. So if it's less than, what direction do we go? Left? Yeah. So what we'll do is, because we're doing this recursively, we will actually just return a call to remove, which is the method we're in currently. and we will pass in our left child as the place to go, and of course, we will pass along the data. And that's all we need to do there. And then that will come back into this method, and this process will go on until it resolves. So the other possibility is if that our data is greater than the node that we're currently looking at, right? In that case, what should we do? Right, so we just need to go to the right instead of the left. Okay? And so then that leaves us with, we've taken care of those two conditions. So now the only condition remaining is we are at the thing that needs to be deleted. So if we're at the thing that needs to be deleted, what do we need to know? We need to know its degree, right? Because we need to know, like, does it have children, and are we going to have to, like, move them around once we take it out or not? So if you remember, we implemented that degree method in Node. So we can actually pull that by simply looking at the node we're in at the moment and calling degree. And that will give us an integer back, 0, 1, or 2. And so now we have access to that here. And we can make our decision on how we're going to go about deleting this. So to do that, I'm going to just start with the degree if it's 0, which is a wonderful case because it means that the node we want to delete, we're there, and it doesn't have any children, and so we can just delete it and be done. And so all that looks like for us is we will say delete the node, and then we will set the node, and remember we have a pointer to a reference here, so we're actually able to set this value to be a null pointer. So that anything that was pointing at it is now pointing to a null pointer. So that cleans that up for us nicely. So that is the easy case of if the degree is 0. So I'm going to do an else if the degree is 1. And you're, like, there are a bunch of different ways to do this stylistically. I'm just doing else if here. I don't really know why, but it's fine. You could choose to, like, do a switch statement if you wanted. You could, whatever you please. So let's think about having a degree of 1, right? So we have 1 child. And all that meant, if you remember, like, visually looking at it, like, we just need to take a child that's below the node we're going to delete and connect it to the node that's above the deletion. So we're just pulling one guy out and connecting those, right? And so what we're going to do is we're going to first get a temporary pointer. So I'm just going to make a temp pointer to the node we're currently at, right? Because we're going to do some work here, and we're going to need to keep a reference to it. And then we need to think about, does it have a left child or a right child? Because if it's only got 1 child, but which one? So we need to check that. So we'll just say if the node's left child is not the null pointer, so meaning it has a left child, then we're going to set node equal to the left. And this is, again, because we have that reference to the pointer, we're actually changing the value of the node we're at to be its own child. And that will propagate up, and it will be fine in the tree. And so the other condition, so I'll just do an else. In this case, this is if it's the right child, right? That's the only other option. So I'll set the node equal to the right child, just like that. And in both of these cases, once I've done that, I'm going to delete my temp node here that I created. And that is deleting the actual node that has that value in it that we want to get rid of. And that's why I saved a reference to it, because I overwrote it in this if statement. So that covers the case of 1 child. So now the next case, and the most complicated of any of the cases, is when there are 2 children, right? And we have some options on what we do there. So I'll just put it in this else block, and remember we're kind of just if degree is 0, if degree is 1, and now our else. And so this is definitely like the degree equaling 2 here. So I'm going to do the same thing first with my getting a temporary pointer. But you remember one of our approaches for this, there were two ways of doing it, right? And let's see. So we could do either the in-order successor, and so that was the minimum value in the right subtree, or we could do the in-order predecessor, which is the max value in the left subtree. Either one's a valid option, and if you remember, we did both of them. So we identify them, and the whole thing here is to swap them around. So like in this case, we're deleting 56, so the minimum value in the right subtree is 57. So we end up copying that up there, and then we just get rid of 57 like that. So to actually implement that, the first thing I'm going to do is make my temporary pointer to my current node that I'm going to delete ultimately, so that I can have access to it. And so I'm going to just go with the left approach here. And so let's see, what was that? So I'm doing the left. I'm looking for the maximum value in the left subtree. And so what I'm going to do is I'm going to just enter a loop. And in my case, so because I'm in the left here, I'm going to go on the right side, and I'm just going to go until I get to the kind of the edge. Like I'm just going to go down that tree. So visually, you can see in both of these cases, the way that we go about it is just kind of going to in one direction. So here, once we're here, we're just in that direction, right? And then the opposite if we're on the other tree. So what that looks like in code for us is to say while our temporary node, which is our left node currently, while its right child is not null, then what we're going to do is just simply go right. So temp will equal temp right. And so that's just going right down the tree until we get to that stopping condition of the child being null, which means we found the leaf that we need to use. So now that we have that, what we can do is we can take our node and set its data equal to the temp node's data. So we found the one we want to swap with it. This is the swap happening right here. And then what we can do is we can simply remove, we'll call remove on node the left child, and we'll pass in that data as well. And so what that will do is rather than us having to like handle the two conditions that remain of like no child or one child, we're just going to call this function that we just wrote, and it will go through it just like anything and take care of it. And so once we've done all of this, ultimately this function returns a Boolean, so we need to return true because we have, not true, because we've deleted the node that we needed to delete. Okay. So let's just check that things still compile, right? Even without adding any test code, let's just see if we've made any obvious errors. So still compiling, still running our really basic, string out test here. So let's go ahead and jump over here into our test file, and let's just make a binary search tree. And then, let's see, do we have an insert? Let's just try calling that and see if like everything breaks. Okay, so we've got our first compiler error, right? And so this is a complaint you can see about the destructor function needing to exist because we are creating this and destroying this thing here, and we have not written that destructor yet. So what we can do if we just want to kind of have things move along here, we can just go ahead and write that, and we don't even really need to fill it in if we just want to just worried about compiling and running. And so I'm just going to leave it blank with a to-do here, and we'll see if that gets us into a better place. So yeah, we're running now and compiling. And presumably we're inserting something into the tree without an issue, but we don't know because we can't see it. And then let's go ahead and just try out our remove, maybe a couple of times. File that. And mostly in this case, like I'm looking for a seg fault to happen in runtime because it's probably going to compile fine. But it seems that that's okay. But we need to be able to actually see like what's going on in the data structure. So let's move on to that. And if you remember, we had different ways of going through the tree to like print it out. We had the pre-order, in-order, post-order approach to doing things. So let's go ahead and just write the in-order traversal so that we can see in the tree. And just like the others, it's got a public method and a private one. So the public one takes in an output stream object, which is cout typically in our case, we're going to pass to it. And all we're going to do in there is call the private one, which will take in a root node, or a node to start with, and then that same output stream. And so we'll pass that along. That's our public one. So let's do the private one, which is where things actually happen. So that's also called in order. And it takes in a pointer to a node and a output stream, a reference to one. And the reason it's just a pointer here is because we don't change anything. So we just need access. We don't need to set anything anywhere. We don't need to worry about that. So I'm going to just do, if the node that we're currently at is not a null pointer, then I'm going to proceed with my in-order traversal. And if you remember, for the in-order, we go left, then we print ourselves, and then we go right. And we do that recursively. So since it's all recursive, this is a nice, easy set of code to write. We can call ourselves in order, and we call it with our left node, which could be a null pointer or anything. Then what we're going to do is we're going to output the value of our own node, so node data. And I'm going to put a space here just so it's readable when we do output it. And then we need to call it for our right side. So in order node right. And we'll pass along that output stream there. And that should be all that we need to do an in-order traversal. So let's jump over to our test file, and we will call in order, and we are going to pass in cout and see if this prints. Well, it should print nothing if we remove that, so let's just comment that out real quick. Okay, so we've printed 12, which is in our, the only thing in our data structure, right? We inserted 12, we tried to remove 1, there's no 1, so it's fine. And we can, test this out a bit if you want, just to make sure it can handle more than one thing. There's your 12, 122. And we removed 1, right? So no 1. So that's working. Let me see what we should. So we've got a few other things to implement, right? But these are the core ones. So what we've got left in our implementation here, and what I will ultimately fill in and post the completed version for you on this. Let me just show you. There we go. Okay. So what we've done. So we wrote the insert, we wrote the remove, and we wrote in order here. So that leaves us with find, which is just traversing the tree looking for something and returning a Boolean. And then our pre-order and post-order, which are very similar to our in order, right? It's just a different, sequence of doing things. And then destroy, which is a way of cleaning up memory and nodes. And so what I'll do is I will post a finished and fully commented version of this for you on Canvas so that you can look at it. And if you have any questions, we can talk about that. Monday we'll move on and start balancing these trees so that they always have a nice property where they kind of have a good runtime. I will see you guys on Monday.